Hi there, I'm Matthew, and today I'm talking about a constructive model of directed univalence in bicubical sets. Right now in computer science, we're at a point where it's actually possible to formally verify large-scale software systems, and lots of people have already done so. One of the challenges is, though, that it takes a lot of time by a lot of experts. From my perspective, one of the main limitations and things that continues to make this challenging is the proof theory that people are using in order to do these projects. And in particular, by changing the proof theory, one could potentially make these projects less expensive and less time-consuming. Directed type theory provides a new setting where one could do formal verification and has the potential to make things much easier, as it has primitives that align nicely with the sorts of structures that we study in computer science. And while that's great, not only do we need directed type theory potentially, but we need a constructive theory. As for these applications, we don't only need to write the proofs, but we need the programs we write to compute. And so, in this talk, I'm eventually going to look at how to define the untyped lambda calculus with scope variables and define how to weaken terms and introduce one new variable in scope. And when we do this, it'll transform this large chunk of code that is not done without using directed type theory and take advantage of directed type theory to translate it into this single line. And what this line says is just asking the type checker to transport terms to those with one more variable in scope by weakening the context. So what is directed type theory? Directed type theory is an extension of homotopy type theory containing both regular invertible paths and directed paths we call morphisms. Our work is an extension of cubical type theory, which allows us to develop a constructive version of directed type theory. So first, let's look at all the type theories we build on. So, the main idea of homotopy type theory is that types are not just sets of terms, but are infinity groupoids, or topological spaces. So in particular, that means that for every two terms, A0 and A1 in a type, we also have a type of paths from A0 to A1. And this path type is a proof-relevant congruent equivalence relation. And also notice, as the path type is a type itself, for every two paths, P0 and P1 in the same path type, we also have a type of paths from P0 to P1, which allows us to represent surfaces. And by continuing this pattern, we can also talk about volumes and higher dimensional volumes. And as path types are congruent, this actually imposes that all functions are continuous as they send paths to paths, surfaces to surfaces, and so on and so forth. Besides that, one of the main features of homotopy type theory is the univalence axiom, which states that the path type for the universe is equivalent to the type of equivalences. So for every path from A to B, we have a pair of invertible functions between A and B. And so univalence is giving meaning to what it is to be a path in the universe. And so cubical type theory takes the ideas from homotopy type theory and structures it in such a way that it's actually constructive and computational. And that means that, for example, for univalence, whenever we have a path from a type A to a type B, we actually get a pair of invertible functions that compute instead of just terms of the function type. And this is possible because cubical type theory chooses a very well-behaved structure to encode the data of paths and higher dimensional paths in the types, and they look like cubes. And so now for directed type theory, as I mentioned before, it's an extension of HOT so that types additionally have categorical structure. So there's morphisms along with the topological path structure. In particular, this makes it so that types, we think of them as infinity categories. And so for every two terms, A0 and A1, in a type, we also have a type of morphisms from A0 to A1. And in this case, it is a proof-relevant, congruent, reflexive, transitive relation. But it's not symmetric, as we can't always invert a morphism. And as before, Hom is also a type, the Hom types. And so we can talk about morphisms in a morphism type. But one thing to notice is that in this case, there's only one dimension of non-trivial morphism structure. So when we look at the Hom type of a Hom type, it's equivalent to the path type of the Hom type. And also, as Hom types are congruent, this enforces that all functions are functors. So they not only send points to points, but they send morphisms to morphisms. Analogously to homotopy type theory, there's also a notion of directed univalence. And it states that for types A and B, the morphisms in the universe from A to B are equivalent to functions from A to B. One thing to notice that unlike in hot and cubical type theory, in directed type theory we actually need to consider multiple universes that contain types and these universes classify different behavior properties. So the first universe we need to think about is the Kahn universe, and it contains fibrant types, which are those that are basically the homotopy type theory types, but they have arbitrary directed structure. The next universe we think about is the Siegel universe, and so all of the types in it are also fibrant, but their directed structure is required to have unique compositions of morphisms, so they behave like infinity categories. And lastly, we have the covariant universe, and it contains fibrant types as well, but they have trivial morphism structure, and so they're effectively infinity groupoids and not infinity categories. However, they depend on all the morphisms in their context covariantly, which means that, let's say you have a dependent type on some category C, whenever you have a morphism in C, you get a function that coerces in the same direction as the morphism between the types that depend on the terms at the endpoints of the morphism. And also, just thinking about what all this means, then directed univalence is stated for ucov, and basically says that the covariant universe is the category of spaces where morphisms are continuous functions. And as a part of it, we have the DUA function that turns a function into a morphism, and the direct coercion function, DCoE, that turns a morphism into a function. So lastly, now moving on to our work, in bicubical directed type theory, we give a constructive interpretation of directed type theory. And again, this now means that for directed univalence, whenever we have a morphism in the universe, we get an actual function from A to B that computes. And as with cubical type theory, this is possible by choosing a particularly well-behaved cubical structure to encode both the path structure and the morphism structure. So we think about things in general as pairs of cubes. And this brings us to the main theorem from our paper, and it is that there exists a constructive model of type theory with both a universe of fibrant types and a universe of covariant fibrations, such that the types in the covariant universe are also in the Kahn universe. The Kahn universe is closed under pi types, sigma types, path types, Hom types, and also contains codes for smaller covariant universes and Kahn universes. The covariant universe is closed under pi types when the domain is a fixed closed type, as in general, if you think about function types, they vary on the domain contravariantly, not covariantly. It's also closed under sigma types, path types, and Hom types. And both the Kahn universe and covariant universe have regular univalence, and the covariant universe also has directed univalence. And also, most of this has been formalized in Agda. Let's now see what using directed type theory for formal verification could look like. So, as we all know, computer science is full of directed structures. And as I mentioned earlier, we're going to see how we can take advantage of this fact when working in directed type theory by defining the untyped lambda calculus with scoped variables, and we're going to define how to weaken terms by introducing new variables into their scope. One thing to note is that to do this, we'll be using a directed higher inductive type. And all that means is that in this type, we're going to have constructors that not only define terms, but also define morphisms between terms. And as a footnote, we have not yet formally studied such types, and we intend to develop a theory of them as a part of our future work. So let's get started. First, we're going to define a type of contexts, and we have an empty context, and given any context, we can extend it and introduce a new variable. Next, we're going to define the type of variables in a context before going to terms. And so in the empty context, we have the empty type because there's no variables in scope. And then in our inductive case, when we extend a context, we have all the variables in our previous context plus one. So in particular, we define it to be the coproduct of the recursive case and the unit type. And now we can define the type of lambda terms. And so first off, we have variables. So in context gamma, for every variable in context gamma, we have a term in context gamma. We can apply two terms to get a new term. And also we can form a lambda by taking a term that has one more variable and binding that variable to get a term in the context gamma. So now, what does this definition look like in directed type theory? Well, we're going to define the type of contexts, and again, there's the empty context, and we can extend a context. We're also going to have one more constructor, and this is our directed higher inductive type, that says that for every context gamma, we have a morphism from gamma to the context with one more variable than gamma that corresponds to weakening. And one thing to note is that we say that context is in the universe of Siegel types because we want it to be a category and thus have unique compositions of morphisms. Next, we define the type of variables. And so, again, we do induction. On the empty context, we have no variables, and thus it equals the empty type. And then when we extend the context, we also just take the coproduct of the variables in gamma with the unit to introduce one more variable. Because we did induction on this directed higher inductive type that has one more constructor, we also have one more case to handle for this weakening constructor. And in order to build it, we need to give a morphism in the universe as covariant fibration, because that's where we're defining the dependent type var, from var gamma to var x gamma. So from the variables in context gamma to the variables with one more in scope. And so how are we going to do this? Well, as we're in the covariant universe, first off, again, we depend on morphisms in context covariantly. And because we're in this universe, we can use directed univalence. And so when we do that now, instead of providing a morphism from var gamma to var x gamma, we instead get to provide a function. And what function do we use? Well, the obvious choice is in left, that one that includes the variables from gamma into the variables from x gamma. And now, let's go define terms. So again, we're going to do it as an inductive type. For variables, we include all the variables. We can always apply two terms to get another term. And again, to lambda extract, we take a term that has one more variable in scope and bind that variable. Again, we're saying that this type of terms is in the covariant universe as it depends on the morphisms of the context covariantly. So now let's try to define how to weaken terms. So doing this without directed type theory, we need to give a function that goes from term gamma to term x gamma. And we're going to do it by induction. In the variable case, it makes sense to just include the variable by kind of using it in left. For the application case, we just weaken both terms. But what about the lambda case? If we went and weakened the term directly, it would actually change which variable was bound by the lambda to the one where the new variable we introduce, which is not what we want to do. We want to keep the same variable bound. So it's a bit more complicated, and we need to actually think about weakening not just at the end of the context, but at an arbitrary location in the context. So let's try again. So again, just here's the type of variables as a reminder, and now we're going to define a type of locations in a context. And it looks very similar to the type of variables, except that it's non-empty, the empty context. And basically, if you notice, this is the locations in context gamma are equivalent to the variables in context x gamma because, for example, when you have 3 variables in a context, there's 4 locations where you could introduce a new variable. So now that we've done this, we can define how to weaken variables first at an arbitrary location. And so if we're trying to weaken a variable in the empty context, there is no such variable, so we can't do anything. If we're going to weaken a variable by introducing the variable on the outermost position, we're always going to include the variable in the left, because the variable we're adding is at the outside. If instead we're weakening somewhere inside the context and the variable we're trying to weaken is on the outside of the context, then it remains on the outside of the context. And if we're trying to weaken inside the context and the variable is somewhere inside the context, then we use a recursive call and go in the context to figure out how to weaken the variable. And having done that, we can now reconsider how to weaken terms by first defining a function that weakens terms in an arbitrary location. And now this works by induction. To weaken a variable, we just weaken the variable. In an application, we weaken both terms that are involved. And now when we go to weaken a function, what we do is we weaken the body of the function, but we shift the location over 1 to the left to make sure that the bound variable remains the same. And now having done that, we can define our normal weakening, where we're just weakening on the outside to be, this function is simply given by using our helper function and setting the location to be the outermost spot. So now that we've done this the standard way, what does this look like in directed type theory? So again, here's our definition of terms. And now, how do we define this weakening function? Well, we want a function that takes a term in gamma and returns a term in the context with 1 more variable. And to do that, we're going to use directed transport, which is just a dependent version of the directed coercion function. And so what this does is it takes a morphism from gamma to x gamma in the type of contexts and returns a function from term gamma to term x gamma. And thankfully, we have such a morphism already. That's, in particular, just the morphism that is given by weakening gamma. So all we have to do is just say, please transport terms using the weakening gamma morphism. And so that's not all we can actually do. So yes, we can weaken terms using this directed transport function automatically without the headache we had before. But for example, let's say we wanted to weaken a term twice, and so introduce 2 new variables at the end of the context. Well, in order to do that, we can actually just transport once, because in particular, we can compose the 2 weakening morphisms into a single morphism and just transport along that. And similarly, what if we wanted to weaken by inserting the new variable in the second position instead of the first position? So like what we do when we go inside a lambda. Well, we also happen to know that all of our morphisms are congruent. So in particular, we can transport along the morphism we get by applying the extend function or constructor to the weakened gamma morphism to get this morphism that we want. And personally, I find this quite impressive because all we had to provide in order to get all of this functionality was an explanation for how to weaken variables once in the outermost position. And yet the type checker and the type theory can automatically figure out how to do all this, and all these functions compute. Let's now take a quick look at how we define this type theory. So, Emily Real and Mike Schulman define a type theory for infinity categories that has a model in bisimplicial sets. And some of the main ideas are that Siegel types and resc types are defined by giving predicates on types that say when a type is Siegel or resc. Similarly, there's also a predicate that says when a dependent type is a covariant discrete fibration. Cavallo, Real, and Sattler have also externally defined a universe of covariant fibrations, and they have proven for it directed univalence, that morphisms in this universe are equivalent to functions. So, now what did we do? We first translated the predicates from Real-Schulman into equivalent ones that look a bit more like cubical type theory and are given by filling problems. We then defined the universe of covariant fibrations using the LICS construction. We then also defined glue types, similar to cubical type theory, but instead of gluing along equivalences, we glue along functions. And we can then use this to hopefully construct directed univalence. And so, first, we're able to define, using the glue type, this DUA function that turns a function between types in the covariant universe into a morphism. We also have the directed coercion function that turns a morphism into a function. We have the DUA beta proof that proves that the function space is a retract of the morphism space. And then the only thing that's left to prove to complete the equivalence is that morphisms are also a retract of functions. However, with this approach, we get stuck trying to prove DUA eta. And so, what happens? So, what we're trying to do is define a path between this morphism P and the morphism we get from the round trip using DUA and DCOE. And given it's a morphism in the covariant universe, we are defining a path in the covariant universe indexed by this directed interval variable I. And thus, given that we have univalence for the covariant universe, this is the same as defining an equivalence. And so, in order to do that, we can first define this DUA eta fun, which is a function from the morphism P at I to the round trip of P at I. However, we are unable to define the function going the other direction, which is what we need to complete the equivalence and thus directed univalence. And so seems like we're stuck. And so, given that everything up to this point has been done in the internal language of Topos, we have also formalized all of it in Agda. And so, now we need to finish directed univalence. So, the proof in the bisimplicial model relies on the fact that weak equivalences are level-wise weak equivalences of simplicial sets. And to emulate this, we're going to take inspiration from the injective model structure in bicubical sets. And the idea is that we're going to think of bicubical sets as functors from the cube category into the type theoretic model structure on cubical sets. So now, thinking about the injective model structure, we're going to take advantage of how Mike Schulman classifies an injective fibrant object. So it's this functor A, C to M, is a fibrant object if it is object-wise fibrant in the model category M, and it is equivalent to its cobar, where cobar is a pointed endofunctor that acts on these functors. So Kakan, Roosh, and Sattler have internalized the cobar construction in a syntactic setting and have actually constructively shown that weak equivalences are object-wise weak equivalences, which is precisely what we need. So, taking advantage of this fact, what do? Well, we add the cobar operator to our internal language, along with the natural transformation it's equipped with, given it's a pointed endofunctor. We can then define when a type is a stack as when this natural transformation at that type is an equivalence. Then we can define a new universe of covariant stacks, which contains all the types in the covariant universe that are also stacks. We can show that the universe of covariant stacks is closed under all the necessary typeformers. And then we constructively prove an external lemma that's inspired by the bisimplicial proof of directed univalence, and add that lemma as an axiom to our internal language, and are able to then complete the construction of directed univalence. So, having done this, we can now look at our main theorem again and see that we have two universes, the Kahn universe and the universe of covariant vibrations, which is in particular those that are also stacks. And the universe of covariant stacks, all the types in it are also Kahn. The Kahn universe is closed under pi, sigma, path, and Hom, and also contains smaller universes of covariant stacks and Kahn universes. And the universe of covariant stacks is closed under pi with fixed closed domain. It's closed under sigma, path, and Hom. And again, the Kahn universe and the universe of covariant stacks are both path univalent, and the universe of covariant stacks has directed univalence. So, lastly, for our future work, while our work is constructive, we still want to develop a computational semantics and actually implement this in a proof assistant. And as we mentioned before, we also want to develop a theory of directed and higher inductive types and add that to directed type theory.